Hello to the fantastic Classiq community. My name is Ron Cohen. I'm an electrical engineer working in Classiq, and my master thesis is in quantum error correction, linear optic and measurement-based quantum computation. In this video, I would like to introduce you to one of my favorite powerful post-processing tools that Classiq gives you, which will allow you to reduce your quantum phase estimation circuit resources exponentially and achieve incredible resolution with synthesizable programs and lower depth hardware. I want to introduce you to the amplitude estimation algorithm to demonstrate that. This algorithm aims to estimate the sum of probabilities of all states we defined as good. It is helpful in finance cases, for example, when we want to estimate our portfolio's risk. Look for a demo in Classiq's user guide. For this algorithm, we use the Grover operator, responsible for distinguishing between the good states and the bad states. Its eigenstates of the Grover operator contain the solution we seek, which is the probability of the good states. To estimate its eigenstates, we use the QPE algorithm. Using QPE, we can estimate eigenvalue of Q, the Grover operator, by measuring the output of the first register. Notice that naively, the resolution of the measurements depend on the size of the estimation register, because the number of possible results is limited. It's limited to 2 to the power of the size of the register, different combinations that are possible in the register, which leads to a quantization error. So, we begin with the injection of the initialized state into the input of the QPE and replace the unitary operator of the QPE with the Grover operator, Q. Once we create the quantum amplitude estimation algorithm, we are ready to execute it on hardware and to post-process its measurements to find the estimation we are looking for, the probability of the good states. Since we know how to analytically calculate the quantum state of the output of the algorithm, we can also analytically calculate the probability of getting each of the optional measurements, which will create the shape of the histogram once we execute the program repeatedly. Notice that the shape of this histogram depends on the parameter theta that we are looking for and on the estimation register size. Now, once we collect all the execution data, we have to estimate the results based on that data. In the naive method, we will pick the result with the highest count, but will inherently create a quantization error that depends on the estimation register size, no matter how many shots we execute the circuit. Also notice that increasing the size of the estimation register in the case of the naive method will consume a circuit that has a depth that is exponential in the size of the register. For example, for error better than 1e to the minus 5, we will need a circuit that applies Q hundreds of thousands of times. Instead, we, in Classiq, fit the histogram data into the expected parametric curve and extract the results with exponentially smaller depths. So we pay in the number of execution shots instead of the depth we gain from circuits that a synthesizer can deal with and fit into today's hardware small depths. Also notice that the problem size, the portfolio size or molecule size, does not affect the needed estimation register size and the num shots that are needed for that accuracy. Now, I would like to demonstrate how easy it is to do it by yourself. Check the amplitude estimation page of Classiq user guide. Here I copied the code from the user guide into my environment. At the left side, the build prog function, you can see how we define the quantum circuits with not many lines. We defined the oracle that affect the Grover operator parameters. We define the state preparation parameters, which is the initialization of the state. So this way we can build the amplitude estimation parameters, which build for us all the algorithm, and it's all set. In the add classical main part, we do sample, which is the repeated executions given num shots, and the post-process part that extract the result. In the synthesize function, we take the model with its classical main, we synthesize it to a program, we can show it to graphically see the circuit, and to execute it and show the results. After synthesizing the circuit and showing it, we get something that look like this. We can go inside and to see how it's implemented, the state preparation and the phase estimation. We can even go inside the phase estimation and to see how it's implemented with the Grover operator, with the actually most optimized circuit that was synthesized from a high-level model language. By executing the circuit, we get the data, which can do now a naive post-process or smarter post-process. So as we saw in the code, we chose the best fit method of post-processing, the smarter way. So here, let's see the results of this post-processing, and let's see how we benefit from it. So I plotted the errors I got for different probabilities measured and with increasing numshots. And as you can see, for this small circuit with an estimation register size of only 3 that can be synthesized quickly and is also able to run on today's hardware, we can get a fantastic resolution by just increasing the number of shots. Here, in this plot, we can see that increasing the num shots achieves a resolution equivalent to much more resource-consuming circuits. By increasing num shots by a factor of 10,000s, we get a resolution equivalent to a circuit that had to be 10,000 times bigger if we were choosing the naive approach, and therefore, perhaps could never be running on any hardware in the following years. Thank you very much for watching. You are more than welcome to ask questions in our Slack community. You can scan the QR code. Thanks.